In this chapter, we look at producer theory. The main goal of producer theory is to understand how firms make decisions about production and input use, and ultimately how these decisions determine the supply curve. The derivation of the supply function will ultimately happen in the chapter on cost theory. We will start with production functions, then move into the distinction between short-run and long-run production, and end with profit maximization. Along the way, we will connect producer theory back to consumer theory to show the parallels and the differences. There are many similarities between consumer and producer theory. Consumer preferences are analogous to production technology. Just as consumers have preferences over bundles of goods, firms have production technologies that determine how inputs can be transformed into outputs. Budget constraints faced by consumers are similar to cost constraints faced by producers. Consumers choose their optimal consumption given their budget, while producers choose their optimal production given their input costs. The big difference is that producers are not constrained to a fixed budget. Consumption choices mirror production choices, and in the graphical representation, indifference curves and budget lines in consumer theory become isoquants and isocost lines in producer theory. One key difference, however, is that producer theory explicitly considers short-run versus long-run decisions. That's not something we typically emphasize in consumer theory. Production is the process of combining inputs to produce outputs. A production function shows the maximum amount of output that can be produced over some period of time for each combination of inputs. Production technology can be applied very broadly. For example, building a chair as output from wood and nails as inputs. You can also think about the production of an exam score in a university setting based on the inputs such as ability and time studying, among others. On the next slide, we are going to look at fertilizer as the input to produce the output crop yields. On the left-hand side, you see on the horizontal axis that you have the application rate of fertilizer in pounds per acre, and on the vertical axis, you have the crop yield. And you can see that as you apply fertilizer, your crop yield is going to increase. Note that in reality, the crop yield does not start at zero, but this is for illustration purposes only. Now, on the right-hand side, you see again a production function, which is marked here. And I have marked also different points. So first of all, everything above the production function is not attainable. And everything below the production function is attainable, but not efficient. Now, what does that mean? Consider this point here. What this shows is that you are using an input level of 100 and you're getting an output level of 100 as well. However, your output level given the input level of 100 could be much higher, a little bit above 150, and hence for the same amount of input you can either increase production, or if the output level of 100 is sufficient, then you could decrease your input level to say 50 or 60. Those type of production functions are important for farmers because their goal is not necessarily to maximize yield, but to maximize profit, given the price of fertilizer and the price of crops. It also has implications beyond the farm. Excess fertilizer use contributes to water pollution, increasing cost for water treatment plants such as Des Moines Waterworks or Citizens Energy Group in Indianapolis. One of the most commonly used production functions in economics is the Cobb-Douglas function. It has the form that you see here. You have Q as the output, and you have labor denoted N here as the input, and also capital. Alpha and beta are parameters, and we will show the importance of those parameters in a bit. Note that what differentiates the Cobb-Douglas production function from the same function in consumer theory is this parameter alpha here. Alpha is total factor productivity, or TFP. It is an efficiency parameter that scales output independently of input quantities. It captures technology, knowledge, and other factors not explicitly explained by labor and capital. This is an important difference from consumer theory. Utility functions do not have the TFP term because they only rank preferences ordinally, whereas production functions, in contrast, are cardinal. They measure actual output, and that matters. The Cobb-Douglas function is also useful because it allows us to study returns to scale. If alpha plus beta equals 1, then we have constant returns to scale. What this means is that doubling inputs doubles outputs. If the sum of alpha and beta is above 1, then we have what are called increasing returns to scale. What this means is that doubling inputs leads to a more than a doubling in outputs. And if the sum of alpha and beta is below 1, then we have decreasing returns to scale. What this means is that doubling input less than doubles output. This distinction is critical in understanding how firms grow and how industries are structured. Now here on this slide, you see a graphical representation of the Cobb-Douglas function. On the left-hand side, you see the three-dimensional representation in the sense where you have the inputs x and y, and you also have then the output, the z, on the vertical axis. Now you can see those contour lines here. Those contour lines represent all the points, all the combinations of x and y that give you the same amount of output. On the right-hand side here, you see a picture that you have already seen or that is similar to what you have seen in consumer theory, where you have here what are called isoquants. Those isoquants, those contour lines, represent all the combinations of inputs that lead to the same level of output. So for example, this isoquant here gives you an output of 7. To illustrate the concept of returns to scale within the context of Cobb-Douglas production functions, consider the following table. You have alpha and beta, which are the parameters that determine the economies the returns to scale. And you see that in the first line, you have the sum is equal to 1. The second line, the 8 and the 0.8 and the 0.4, you have the sum of bigger than 1. And then the last line represents decreasing returns to scale. In the first example, we have labor and capital both fixed at 10 and 20. And in the column Q, you can see the output from those input choices. Now, if we are doubling the output, if you're doubling the input levels, so if labor goes from 10 to 20 and capital goes from 20 to 40, then you see here in this column, you see the production, the new production. You see that with constant returns to scale and doubling of the input parameters leads to exactly a doubling of the output parameters, of the output quantity. Whereas if we have increasing returns to scale, then a doubling of the inputs leads to a more than doubling of the outputs. And vice versa, you have an increase in the outputs by less than 2 if you are increasing the inputs, if you're doubling the inputs in the case of decreasing returns to scale. When studying production, we distinguish between the short run and the long run. In the short run, at least one input is fixed. A restaurant, for example, cannot easily change the size of its rented space in the short run, but it can change the number of cooks and servers. An airline cannot easily change the number of planes, but it can change the number of pilots and flight attendants. These fixed inputs, such as factories and machinery, are typically classified as capital. Variable inputs, such as workers, are labeled labor. In the long run, all inputs are variable. Firms have full flexibility to adjust both capital and labor. Now here, we are looking at the short-run production function, and we derive this from a Cobb-Douglas production function. So consider the following production function, where alpha and beta are set to 0.5, and the total factor productivity factor is set to 10. Then, if capital is fixed at 9, then the short-run production function is simply 10 times the square root of 9, which is 3, times the square root of L. And hence, 3 times 10 is equal to 30. and hence the short-run production function is written as Q equals 30 times the square root of L. Or more generally, you have Q as a function of fixed capital and labor can be adjusted. Now, next we are going to introduce the average and marginal product of labor. The marginal product of labor is the additional output produced from hiring one additional worker. We are abbreviating marginal product of labor with MPL. Note that the little delta sign here means the change in. So the marginal product of labor is the change in the output over the change in input. The average product of labor is the average quantity per worker. This is abbreviated with AP, and it is simply Q over L. Note that there is also what is called the law of diminishing marginal product. That in general, as more input is added to a fixed amount of other inputs, its marginal product eventually declines. Now let us look at the graphical representation here of the marginal and average product of labor. Note that on the left-hand side, you have the production function, where you have the input on the horizontal axis, output on the vertical axis, and you have this production function here. Then the average product of labor is you take a point on the line, on the production function, and then the average product of labor is represented by the connecting line to the origin. This is very similar to what you have seen in high school, where you have the rise over run. So rise represents the output, over run represents the input. Okay? So the slope of this connecting line is the average product of labor. The marginal product of labor is simply the slope of this line here, or the slope of the production function. And you will see that you have a point up here where the marginal product of labor and the average product of labor are identical. This is the line, this is the point that you see here on the right-hand side, which shows the average and marginal product of labor. I have mentioned before that there is an analogy between the budget constraint and the ISO cost lines of the producer. So let us consider the ISO cost lines next. So let W be the wage per worker or per unit of L, and let R be the rental rate of capital per unit of K. Then the total cost of production given a K and L can be written as the total cost equaling the wage rate times the number of workers plus the rental rate of capital times the units of capital. Note that you can also change this in terms of the notation, that you can solve this for K. You will see that we are going to soon show a graph where we have K on the vertical axis and L on the horizontal axis. But note that the slope of this total cost, of this ISO cost, is actually determined by the ratio of the input prices. Next, we have to talk about the so-called marginal rate of technical substitution. Note that put in very simple terms, the marginal rate of technical substitution is the rate at which a firm can substitute one input for another while keeping output constant. So what that means is the marginal rate of technical substitution is simply the slope of the isoquant line. Now here, this is something you have seen similar in consumer theory, is the optimal production choice of the producer. So here you have the isoquant line that shows all the inputs of capital and labor that give you the same amount of production. And in order to determine how much capital and how much labor you should use, you are setting the ISO cost line tangent to the isoquant line. Okay? And remember that the slope of the ISO cost line depends on the ratio of the input prices. So if, for example, the input prices were to change in the sense that, for example, labor becomes more expensive, then what this means is that the slope would become steeper and the tangent would probably be more like here, in the sense that you're now substituting away from labor and are using more capital. So this video gives you a very short introduction into producer theory, and I invite you to watch the older video on producer theory, where we are getting much more into the technical details.